known throughout the industry for his honest, dedicated, and work ethic. Mark has developed a reputation providing his clients with knowledge, unbiased guidance, and advice. Mark continues to head the company, which we're going to hear about, steering its business development, innovation, and safety council. Mark also personally supports many R&D projects and sustainable fuel initiatives for the general aviation industry. And Mark, I very much am looking forward to your talk.
So hello, everyone. Again, my name is Mark Kalus, and I'm the president of Aviation here in Montreal. And I just want to take a quick moment to thank the folks at CANEX 2025 and for inviting me, and for Tim for moderating this great webinar. Thanks so very much. So as you mentioned, CASI is a part of Hexagon, and we have a fleet of multi-engine aircraft that are uniquely modified to accommodate many types of sensors for all of our customers. We're a Canadian air operation, and our operations are approved throughout North America, South America, Central America, including the Caribbean, and we've recently added Europe and Africa to it. So I want to welcome everybody to my little presentation that I like to call Aerial Survey 101. I just hope to offer a little bit of insight on the complexities of not only planning for an aerial survey project, but also evaluating the right aircraft for the right job, and always with a strong view of safety. So as Tim mentioned, just a little bit about myself. I am a commercial pilot and aircraft maintenance engineer. And before getting started today, I kind of like to look back a bit on the good old days. I started in the industry back in 1980, and I look back to my first deployment, which was in the South Sudan in Africa. And believe it or not, we had the same type of aircraft we're still using today. Back in those days, we didn't have GPS. We navigated either with an old Doppler system or just looking out the bubble windows, looking over the ground to identify features, while I was reading a rolled up mosaic map with a line drawn on it, telling me where I'm supposed to be. Even the high altitude photo jobs that we did with the same unpressurized piston powered aircraft at 30,000 feet plus, all we had was the drift site to navigate with. And I often remember being in the Arctic, and the aircraft up there, they were still equipped with backup celestial navigation using a sextant. So now I was never really trained for it, but I always admired the old timers who still knew how to use that celestial navigation. So basically, a lot has changed in the business, especially with the advancements in the sensors and the equipment technology, but that hasn't automatically translated into the same advancements in aerial safety. So today, we just want to look at how everyone in this audience can contribute to the process of aerial collection with safety in mind. I guess I can push this button here too, can I? So listen, the first part of any project is gathering information, sharing of critical information about the area of interest so that we can all evaluate the project. We have to ensure that we've considered all the variables and the complexities of the project. As the aircraft provider, we need to know what equipment is desired so we can consider things like the weight of the equipment, the power requirements of the equipment, the size, and other issues, just to ensure that the aircraft can accommodate the equipment and safely operate in all conditions, especially in emergency situations. So this slide just kind of shows a quick look at all the pieces of information that we generally have to get before we can even start the process. So, at the very beginning of any project, it starts with activating what we call our job safety analysis. Some people call it a risk safety assessment. So we need to get all that information about the topography, the location of the area of interest. We always like to get like a KML of the block so we can look over the Google Maps and see exactly what the area looks like. Now, once we get the KML, then we can overlay the flight lines onto our aviation maps. And that helps us so we can look over any restrictions that we need to know about, any protected areas. There's some of the restricted areas, they're called TFRs, temporary flight restrictions, obstacles in the area, challenges that we might have if we have to consider emergency landing sites, and where's the closest airports to operate out of to get into the area of interest. So I want to talk a little bit about these restricted areas, because the TFRs seem to pop up at the worst possible times. And when they're active, they prevent us from flying basically in the ground until the area clears. So here's a good example of a temporary flight restriction. I think you'll all recognize the Washington, D.C. area. I remember we did a project, a bathy project over the Potomac River, and that basically that survey took us right over the White House. So the preparations needed to get permissions for this type of flight were so complex that it even included flying with an armed security agent. And he also reminded us that he was authorized to take extreme measures if we decided to do something crazy over the White House. So needless to say, the planning for this project was intense. But we're also seeing a lot of challenges coordinating with air traffic control and the various government authorities. Often our projects are close to built-up areas. Those built-up areas have airports close by. And as luck would have it, when the weather is good for collection, it's also good for all the other air traffic. And so we're often right in the path of the airlines taking off and landing. So here's an example of what we see as the pilots on some of our screens when we see all the other traffic that's around us when we fly. And so you can really see how congested it is. That you can sort of see the little blue airplane over on the left side of the slide, and that's us in the airplane. So, needless to say, getting the cooperation from air traffic control is paramount in many of these situations. And what we're seeing is becoming imperative that our end clients, the folks that are putting these surveys out for tender, whether they're provincial, federal, or state authorities, we need their support in providing what we call support letters. So these support letters will identify the agency who's asking for the survey and why. This opens the door for the dialogue that we can have with the authorities and start to give them the information that they need so they can accommodate our flight. Now, it's funny, when we talk about accommodations, I'm reminded again, when we were flying an area over Los Angeles, and air traffic control was able to do an unimaginable accommodation for us. And if you look at this screen here, you can see us flying, and you can see all the airlines that they had to route around us so that we could stay online. So believe it or not, ATC was incredibly accommodating. Now, this isn't always the way, but it sure is nice when we get that kind of help. Now, in contrast, the Canadian airspace is becoming increasingly difficult as we're seeing staff shortages, especially during favorable weather, and it's really becoming a challenge. That support letter that we get from the government agency will definitely enlighten the controllers and tell them of the importance of what we're doing. But pre-planning doesn't often work. I remember contacting the manager of an air traffic control region with my support letter, telling him what it is we're doing and why. And he says, I don't care if the Queen of England writes it. We're too busy to accept a survey flight in your zone today. So despite having good weather, we couldn't fly that day. So that kind of coordination is becoming really, really challenging. So when we get the parameters of the job from our clients, we really like it when they give us this kind of detail. They'll tell us all kind of information that we need to know about the flight plan that they've made. They'll give us their ground speed limitations, the flying altitudes that they're requesting. They'll give us indications about the highest obstacles and the lowest terrain clearance. It really helps us so that we can really picture what it is that we're going to be asked to do in the airplane. Now, we're often seeing with clouds restricting us on so many jobs, many of our customers will give us two flight plans, primary and the secondary. And the secondary flight plan is a lower flight plan. And it's interesting because this will allow us to fly, get underneath the clouds, but there is going to be some compromises to it. So the lower flight plan, we have to look at the risk assessment for both altitudes when we have this option. But remember, when we're flying lower, it means more flight lines. More flight lines means more flight hours, and more flight hours means increased cost. But, often getting the collection done on time outweighs some of those increased operational costs. So with the information that we've gathered at this point, we can continue with our pre-risk analysis and see the potential issues. So, the comment here is always be prepared to be caught off guard. And that's exactly what we're faced with in a lot of cases. So the next phase that we have to do is we have to evaluate what equipment are you asking us to put into the aircraft. Now, often we don't get a lot of information other than the general weights and dimensions, but that's becoming more commonplace now. So if you have a look at this equipment that we're asked for, this is the Leica Hawkeye deep water bathymetric system. And when you look at this system, it's fairly large, requires 2 large format camera ports. It's going to need a pretty fair size airplane to accommodate the dimensions and the weight. And we're told that it has an enormous electrical power requirement. We also need to receive the technical specs for the system that includes the safety data sheet. And that's just to make sure that the standards for that equipment are suitable, not only for the installation in an aircraft, but the connections with the aircraft power. From this, we prepare the aircraft, and here's what it looks like when we get it in the airplane. And it's pretty tight, but it all gets in there and it all fits safely. And I'm sure when you look at that, you're probably wondering about egress, saying, you know, how does the pilot get out of the airplane in an emergency? Well, we even thought of that too. Our airplanes have got extra doors installed. That one in the front is an extra emergency exit just for that purpose, to be able to do those kind of jobs. So, you know, after we've gathered up all this information, we're now ready to get into a more in-depth job safety analysis. And that's really to establish if there are any risks that may have possible limitations, not only on the aircraft, but on the crew when we perform these missions. And this is what we use to identify the safety risks, but more importantly, trying to find ways to mitigate the risk. So during the process, we believe everyone should be involved in this analysis process. So because it gives a whole lot more visibility and understanding amongst all the parties for the project, so we can interact and react as a team when the challenges are encountered. So let's take a moment and just recap what have we done so far. We've identified the area to be flown, the topography, some of the risks, the heights to be flown, whether we have a high flight plan or a low flight plan, the ground speeds that's required. We've identified the equipment, and we know what kind of an airplane we're going to need to get all that in. So the next phase is let's go shopping and let's see what kind of airplane we can get. So there's many choices available when it comes to your aircraft provider. There's old aircraft, new aircraft, piston engine aircraft, turbine powered aircraft, single engine and multi-engine aircraft. But what I want to look at today is really to evaluate the aspects of single engine aircraft versus the multi-engine aircraft. So when we look at the aircraft selection, you know, there's a bunch of characteristics that we can pretty much assume from the both types of aircraft. The single engine aircraft are typically going to be lighter, more fuel efficient, lower operating cost, easier to maintain. They're going to come with some disadvantages. They might not be able to carry big equipment. They might not have the power capabilities. They might not be able to handle adverse weather when they have to transit to different areas. And there's going to be a vulnerability to that one engine should it fail. The multi-engine aircraft, the redundancy with the power plant gives a lot of extra safety factors, often greater payload, better performance in some cases, and better adverse weather capabilities if we have to get to an area of interest in a hurry and there's weather in front of us. Often the multi-engine aircraft will have better capabilities for adverse weather. Some of the disadvantages, multi-engine aircraft are going to be more complex, requiring a lot more maintenance. Fuel consumption is going to be more when you consider 2 engines versus 1. There's a greater cost affecting some of the decision making. So now we have seen a lot of advancements in engine technology that have really brought the turbine engines into the single engine capabilities, and it's greatly changed the landscape when you're deciding on a single engine option. And so I'm sure that a lot of you have seen this type of aircraft, for example, the Cessna Caravan. So of interest, though, the turbine-powered aircraft often burn more liters of fuel on one engine than both of the piston-powered aircraft do combined. And we need to consider that when we look at the balance between the cost of the operation and the comparison with the models. We've seen projects that we've been on with turbine-powered aircraft, and they may be restricted to around 4.5 to 5 hour flights, whereas the piston-powered aircraft can get maybe 6 to 7 hour flights because of the difference in fuel burn. We're seeing many areas, both in Canada and abroad, where the gas for piston engine aircraft, called avgas, is not always reliably available. The biggest reason is really the increased environmental challenges relating to the transportation of and the volatility of the fuel. Avgas is more volatile than jet fuel, so it's treated differently as a hazardous material. Both fuels are very flammable, just one is more volatile. So, we often assume that the airports we're going to operate of that say they have fuel, we always now are routinely calling the airport for a couple of reasons. One, to be sure they actually have the fuel they say they have. And two, to see how long it takes to restock the airport supplies for fuel. And this is a challenge for both types of fuel, as the transportation of the fuel, especially to smaller airports or remote areas, is getting limited. Although cumbersome, the situation is not prohibitive. In many areas, we actually have to ship fuel in drums, and it takes some pre-planning to have the fuel on site when the weather opportunities are there. But I can tell you, we've been able to arrange fuel for practically anywhere in the world. It just takes good organization and pre-planning. And now, when jet fuel is the factor and that you've considered, and twin engine is considered the safer option for the project, we now have a twin engine turbine powered aircraft with our newly acquired Britten-Norman Defender. And the twin turbine aircraft, does come with increased cost, but the added safety with the turbine engines and the twin engine can outweigh the cost on certain projects. So fuel is becoming the biggest consideration these days for choosing the right aircraft. So some of the factors that you want to look at to influence your aircraft choice. We talked about some of the operational challenges. If you have to get to an area of interest in a rush situation because of some weather anomaly, and there's weather in between, sometimes you have to consider if the aircraft is capable to get there in a hurry. Fuel requirements, obviously we just talked about that, what type of fuel is going to be readily available in your area. Looking at the terrain is going to be a big factor. Over water surveys has specific requirements, and flying over mountains and big treed areas is going to be something that you have to think when you're choosing the right aircraft. Electrical load is always going to be an issue. Single engine sometimes don't have the same kind of power requirements as a twin engine that'll have two sources. However, they are having a lot of modifications on single engine that have backup systems, although they are dependent on the engine being running. The multi-engine aircraft, can accommodate, a lot more systems at times if they're bigger and more powerful. And I always recount a job that we did down in Haiti, and it was my personal record. When we were down there, we operated 5 different systems at the same time. We had LiDAR, thermal imaging, hyperspectral, and some cameras working all at the same time. So when those kind of jobs are up, you need to know, you need to have an aircraft that has all that capability. And then, of course, factors, regarding to cost and budget constraints is also going to be a big factor when you're evaluating the right aircraft for the right job. So when we look at some of the safety concerns, when we look at single engine, the single engine having only one engine does have limited options for remote and hazardous terrain, things to think about, especially complications over the water if you were to have an engine failure. There's going to be sometimes single engine will have less operational capabilities or to get to the areas that you need to get to. We talked about electrical load constraints. One of the other things we think about often is our friends that we share the air with are birds. Birds have always been a problem for us aircraft. But if you had a single engine one and if you look at the slide I'm popping up here, a bird strike in the nose of the aircraft where the engine is could have quite a damaging effect on the operation of the engine. So there's a little bit more risk to consider when we talk about bird strikes. And who would have thought that recently we're also talking about drone strikes. Down in California, we saw an aircraft get hit with a drone. So these are now becoming pretty big considerations that we have to think about and try to mitigate it in our safety analysis. Multi-engine aircraft, safety concerns, they're definitely going to be higher maintenance. They're going to require a lot more operational costs. And some of the areas that we operate in, when you think about hot, damp, corrosive environments, it's going to create a lot of mechanical issues for a multi-engine aircraft that has more complex systems. The operating cost is a big part in decision making. When you look at an aircraft that has 2 engines, the pilot training required to handle asymmetric thrust if you had to fly in one engine is going to change. So you need to have that kind of training and that risk of being able to handle the aircraft when it loses an engine to fly on one engine. So some of the performance risks are going to be, and often when we talk about multi-engine, we talk about the risk of being on one engine. So let's just take a look at talking about a multi-engine aircraft. So as soon as we select multi-engine, it doesn't mean it's a catch-all to end-all for the safety risks. Not all multi-engine aircraft are the same. Most multi-engine aircraft are considered capable of maintaining altitude on one engine. But when you consider risk mitigation, that's not really enough. We need to consider if an aircraft can climb on one engine. So we often have obstacles or hills to climb to get our way back to the airport. So a multi-engine aircraft on one engine needs to be able to climb. And when we consider an aircraft's capability to climb on one engine, we always need to consider the worst case scenario, not the best case. The worst case is you're at full gross weight, you're in very hot conditions, and that's when you lose the engine. So when you look at that, we have to be sure that the aircraft can climb in those conditions. So let's take a look at some graphs and see what we're talking about here. This graph just simply illustrates you've got an aircraft that's operating out of an airport that's 3,000 feet above sea level. The temperature is plus 30 degrees Celsius, kind of hot, and it's at full gross takeoff weight. So in this graph, we can see that if we were on one engine, our climb would be about 90 feet per minute. Not bad, it's at least in the positive, but it may not be enough in all situations. Here we're operating down in Costa Rica, and so in those kind of temperatures, 90 feet a minute might not be enough to really get what we need. So how can we mitigate that? What can we do? So there's a couple things that we can do that can affect the performance on one engine, and that's within our control. And so if you think about the two items, it's weight and temperature. So in the same graph, if we look at reducing the weight of the aircraft, maybe taking out some non-mission critical things, maybe reducing some fuel if we had to, but getting the aircraft lighter by as little as 500 pounds, we can gain another 80 feet a minute climb on one engine. That definitely is an improvement. But then if we also think about temperature, that's in our control. If you think about if we chose to fly earlier in the morning when before the temperatures get too hot. So the same situation, by just reducing 10 degrees on the same flight and the same conditions, we can get close to 200 feet per minute climb on one engine. So that's definitely an improvement and definitely something to consider when you're working with a multi-engine aircraft. One of the other critical aspects that I like to talk about with aircraft operation is to emphasize flight watch while the aircraft's on site. I've often thought, it'd be really bad to have a forced landing in a remote area, but it'd be even worse if you couldn't find me. Many people use commercially available programs to track the aircraft, like Flight Radar 24, which is an ADS-B-based system, but ADS-B has outages, and it works on the aircraft's line of sight with ground-based antennas. So we see many gaps, and there's nothing more heart-stopping than seeing the aircraft on the screen disappear. So it's important to have satellite-based tracking systems that use like the Iridium satellite system. This ensures that the aircraft that we have visibility of the aircraft while in flight anywhere in the world. And I believe that everyone involved in a project should take part in flight watch. You can see that at any given moment, you can see the aircraft's position through latitude and longitude. You can see its altitude. You can see the speed that he's at, and you can see the heading he's on. So this way we can pinpoint the aircraft's location at any time if a rescue is required. So just to kind of sum up some of our conclusion and some of our recommendations, looking at single engine aircraft, they're often more cost effective. They do have some higher risks in some areas, especially over water and high risk airspace. Multi-engine aircraft have safer redundancy systems, but increased complexity and cost. Size, weight, electrical load capacity needs to be verified when you choose your aircraft. The operational terrain you're going to be operating is going to be critical for your survey to decide which is the right aircraft. And bird and drone strike risk certainly highlights the benefit of having some of those redundancies with your engine systems. So recommendations, we always recommend to start every project with a detailed and a cooperative job safety analysis to identify all risks. Tailor your aircraft choice to the mission needs and the terrain. Invest in training, especially for water-based emergency scenarios. And don't let the cost outweigh the various safety considerations. My final thoughts is just safety really is a proactive effort. It has to balance your operational efficiencies with preparedness. The best preparations are achieved through a good cooperative job safety analysis and risk sharing. And the cost of an expensive aircraft, when you think about it, with an expensive sensor, is nothing compared to the price of the safety of our crew. My dad always said the 3 best ways to be sure the job gets done is to prepare, prepare, prepare. So that wraps up my my little presentation, and then I'll just hand it out to the floor to see if there's any questions.
That was a real informative talk. And, you know, perhaps there's a lot of end users of LiDAR out there that aren't, you know, never really think too much about the, you know, what aircraft was used for some of these big surveys and so forth. So you've really enlightened us in terms of some of the differences, the considerations, and so forth. I especially liked your example there of the, you know, assuming you're only on one engine, how much lift can you have, and the consideration of weight versus temperature. Real interesting stuff. Anybody with questions, please put them in the Q&A spot. As we wait for somebody to do that, Mark, you mentioned a few times there about considerations over water. And obviously we fly a Topo-Bathy system, and sometimes we need to go out to fly you know, an island that is offshore and so forth. Could you just talk a little bit about what the regulations are and the recommendations are around jobs such as that, where we're in the flying around water?
Yeah, that's a great question. The worldwide recommendation about single engine aircraft over the water is looking at the glide distance of the aircraft at that altitude back to shore. So if you think about the average Bathy job, we're flying at about 1,200 to 1,500 feet. The glide ratio for a single engine airplane is really only about 2 nautical miles. So after you're beyond the shore of more than 2 nautical miles, if you had an emergency and you lost your engine, you are probably not going to make it back to shore, in which case you really have to consider that you're going to be making a forced landing on the water. And so any of those situations, every aircraft in those situations, you should have on board like a life raft for your crew to be able to handle the crew that you have on board. I always make sure that my crew have wear their life jackets. Don't just have them on board, wear them. You don't want to be fumbling around for that if you did have to make a forced landing. But then if you think about flying over the water, what kind of water? If you did end up doing a forced landing in the water and the water temperatures, like in Florida, was pretty warm, you have the time before hypothermia sets in. You have time for a search and rescue. You have time to find your way and get into your raft and be able to hang out until somebody comes to get you. Up in northern Canada, off the shore of Norway, something like that, water is very cold. So in those cases, you know, we even have to wear suits for that.
Survival suits?
Survival suits for that, exposure suits for that. Because if you did have to do a forced landing in the water, you don't have a lot of time to get yourself organized. So when we're preparing for jobs over the water, especially with Bathy, the best thing you can do is really prepare yourself. Have your risk mitigated, have good training. Imagine some of the single engine aircraft that you're operating have a fixed gear, and depending on the seas that they're touching down on, and that gear digs in, that aircraft might flip over. So are you guys trained to be able to get out of the airplane, find your way with an airplane possibly submerged upside down, get out of the aircraft, get into your life raft, and get yourself organized? So that's all about training. We call that egress training. So the advent of all this improvements on engines has really gotten the turbine so reliable that we've become a bit complacent when we think about going over the water. But one engine is one engine. So the best thing you can do is really prepare yourself for any of those kind of emergency situations. The multi-engine, yeah, as long as the aircraft has the performance and can can climb on one engine and make it back to home base, the multi-engine does give you a lot more coverage, and especially depending on the kind of water you're going to be operating around.
Right. I see here we have one. Mark, you mentioned a lot of things that are helpful to have when planning a mission. Is there anything that you wish project planners, managers provided when coordinating with you?
Well, like we talked about, like the biggest thing is as much information as we can possibly get. In the past, I got to tell you, when I first got into business, we got surprised a lot. Just show up on site, you'll be fine. It's a job that's easy to do. We get to the job, we find out the terrain, and a lot of the areas that we fly around don't have the kind of maps that we have here in North America. And we've arrived at these sites with very little information that we can use. We get there and we look at the terrain and say, my God, man, that's not an airplane job. You need a helicopter to do that. And so there we've gone and positioned the aircraft all the way there, and we're not really able to do the job properly, or we have a lot of challenges. So definitely that kind of information in advance, so we can really pre-plan to make sure we have no surprises when we get there. And the other thing that we've been caught off guard, and that's where that 2 flight plan rule, when we had 2 different flight plans, we ended up on a job, and it was down in the Caribbean, and it was on an island that was not a whole lot of relief information for us. The flight was going to be about 5,500 feet. We had lots of clearance for obstacles. When we got there, the locals said, did you not know the clouds never raise above 2,500 feet? Yeah. How come you're down here thinking you're going to do a job at 5,500 feet? So immediately we had to force, with the planning, suddenly, on the fly, our client pushed down to about 2,500 feet. 2,500 feet, if we had known that in advance, we might have maybe pre-planned a few things. And I'll tell you why. At that altitude, you're getting much closer to the ground, not much closer to obstacles, but more importantly, much closer to where the wildlife hang out, the birds. So right. Sure enough, we were in the area and we did get hit with a bird. Now, if we had have really pre-planned for that, we might have had maybe a second pilot to look out the window for birds or obstacles while the pilot's flying. You're pretty busy in those kind of environments. So again, the more information we get to talk about the job, and the more criteria, and we talked about speed as well. Often they'll say the speed is normally between 120 and 140 knots. But then when we get there, they say, well, what we really want is 120 knots or 100 over the ground. Well, that's very hard sometimes for an aircraft with the wind. So a lot of those things is really clarifying the parameters of the job before we leave, so we're well prepared for it.
Communication, communication, communication.
And like my dad says, prepare, prepare, prepare. So yeah, you got to prepare for everything. So
great, Mark. I see another one here. What recommendations would you make for a company acquiring a new aircraft for Lidar acquisition? Which single engine and twin engine aircraft would you consider the best in terms of safety, operating costs, and overall efficiency?
Well, that's a great question, and I mean it's like the age-old question, especially when we're talking about survey. So the single engine, if we cut to the chase, especially in Canada, depending on where the area you are, when we get up into the high north, there's very difficult times to get the avgas that we need if you're going to choose a piston engine aircraft. So that is becoming one of the biggest factors. If you're regularly going to be working up there and fuel is going to be a problem, you might go towards a turbine power. Right off the bat, getting a turbine powered aircraft is going to be more cost to buy. Fact. So we've chosen an aircraft that balances cost, efficiency, performance, and reliability with our multi-engine Navajos, for example. They're also turbocharged, so we can get up high if we need to. And but they're subject to getting avgas. So we've had challenges. If the single engine is an option, which definitely reduces a lot of the cost, a lot of the maintenance cost, then you really got to think of, if it's going to be turbine powered, it's going to be a lot of money to buy it. And not only that, a lot of money to put the mods in it to be able to put the sensors in. So depending on the job, depending on the speed requirements of what your system is, the kind of altitude you're going at, you really got to be very careful about which aircraft you choose. The Caravan's been a fantastic airplane for single engine, and the Navajo is the industry standard. Like I said, back in 1980, when I got in the business, there I was over in Africa. What was I working on? A Piper Navajo, the exact airplane we had today, 45 years ago, So those are the aircraft that stand the test of time. But there is a lot of aircraft coming out now. Again, cost is a factor to buy them, but there are a number of multi-engine aircraft that are coming out. They're smaller, very efficient, and very reliable. But the cost to buy them is the factor that you got to think if you've got the budget to buy the aircraft, the capital outlay.
Great. Well, it's not often we get a man of your experience and wealth of knowledge that we can ask these kind of questions that I imagine to a lot of LiDAR users there, again, not necessarily things they think about, but anybody with a sensor or anybody that is very interested in how does it all work? How does the sensor and the aircraft provider come together? How does the planning work? How does the execution happen? And of course, as you described, there's always surprises. There's always, low clouds, bad weather at this area of interest. Let's go to this area of interest. That's what also fascinates me is the amount of flexibility that actual operations teams have to go through. And obviously, being a LiDAR operator, they can make suggestions, but ultimately it's up to the pilot where they fly and how they fly. So it's great to have a good team. I know that is a key aspect of getting a job done efficiently and effectively, and with safety as the number one concern.
Yeah, that's great. Great points, because when you think about it, it really depends on what area you're going to be flying. In our case, we have to provide a service pretty much anywhere around the world. So you have to have an airplane that can get there. Mm-hmm. And if there was a disaster and somebody needed us to deploy urgently, very quickly, we might have weather in between. You got to have an airplane that has the all-weather capabilities to get to that disaster site in a hurry to provide the services that your client's asking for. So, it's really hard to just generically say what's the best airplane to look at when you get into the business. You really got to think of where you're going to be doing, what kind of work are you going to be doing, and put all those pieces together. Because in the case of us, we've got to fly pretty much anywhere at any time and practically overnight. So you've got to have the right aircraft and well equipped to be able to get there when the client is demanding it, especially in those kind of disaster situations like hurricanes and whatnot. So.
Yes. Here's a quite a specific one. What is your opinion on a Avia? I'm probably not pronouncing that right. A P.68 for acquisition.
We know that aircraft. I've often thought about the Avia, and what's kind of funny is I looked at the Avia years ago because it had even turbine engine option. So the thing about the Avia and is with any aircraft. The reason I didn't buy one is because it was too small, and it's just a fact. If I'm going to be able to carry very large systems, we looked at that Hawkeye deep water system. That won't fit in the Avia. That's just a fact, and the engines are smaller, so they might not have the kind of power requirement. So the Avia is a great little airplane. It's been a stalwart with doing all kinds of highway patrols and stuff like that. It's very economical to run. It's 2 engines. You can get the turbo version, so you can get up a little higher. But everything is just about its weight carrying capability and its ability to get somewhere. It's a fixed gear, so it might take a little while to get to where you want to be. But it's a great airplane, very stable, and can get in and out of a lot of little strips. So it's a neat airplane. But again, if you're considering all different kinds of equipment, then you better think of an airplane that has the weight carrying capability and the power to fit it all in and to operate it. We looked at some airplanes. By the time we put the equipment in, we couldn't have any fuel. We didn't have enough weight to put any fuel in. We carried the system, but you couldn't get anywhere with it. And we put long-range fuel tanks in our airplanes, and that's just horrific weight when we start adding more fuel. So the more fuel you add, the less the system you can carry. So trying to find that right balance, it's a challenge. That's probably the biggest part of the job, is to analyze your needs and find the right aircraft for your mission. It really is a bit of a specialty, and I sort of pride myself in that. That if the client comes to me, give me all the parameters. I'll give you the pros and cons of which aircraft can and can't do what you need it to be done. So.
Yeah, no, I bet. So Mark, what is your fleet? Like how many aircraft do you folks have?
Well, so we've got the Navajos, both the smaller ones and the larger Chieftains. So we got 6 of those.
Okay.
And then we newly acquired our Britten-Norman Defender. That's a turbine-powered twin engine. And that was really acquired for a very specific need. So we believe operating up in the Arctic on those gravel strips, doing bathymetric for that coastline up there, we're going to need an aircraft that's uniquely equipped for that. We bought it for that type of project. Going over the water, we've got long-range fuel tanks. We can have a range of almost 10 hours with that aircraft. So when you're operating in very challenging environments and you have a very small window of opportunity to collect, we wanted to have an aircraft that could capitalize every minute of availability we had. And the maintenance on that is fixed gears, so it's very reliable. We had plans up in the Arctic where we have 24 hours of daylight in the bathy collection season. We can basically run 3 flights a day, all night long. It's 24 hours of daylight. So having an aircraft that has those kind of capabilities is what we're looking for. So, but it's very specific. It's kind of slow. So if we had to get all the way to Australia, it's going to take a while to get there. It's just not that fast. So if you're looking for a collection that's higher, fast flying up at high altitude, it's not the airplane for that. So so again, it was very specific for the need of a very specific client and a very specific mission set. So looking at the right aircraft for your right job is really a big challenge. It's a big exercise.
Yes. Well, Mark, I don't see any other questions. So again, thank you for the really informative talk. Lots of interesting things that maybe our audience hasn't thought about too much, but I'm sure we've all coming away a little smarter and a little more knowledgeable.